Okay, we're live. Hi, everyone. My name's Daniel.
Hi, I'm Jesse.
We're going to show you guys some Sonic Pi code that we've worked on together. I say together, Jesse has actually written most of this. And before we really get into it, Jesse, could you tell the good people a little bit about what Sonic Pi is?
Sure. So Sonic Pi is this software that you're seeing on the screen here. It's basically an environment in which you can write code that generates sound and music. Yeah.
Okay, cool. So should we go ahead and let everyone listen to it first, or do you want to talk about it beforehand?
Let's do a listen.
Let's give it a listen. All right. Let's. Do you want to take it to like T? I don't know, 20.
Okay.
All right. So let's get into the guts.
Okay. You drive. Like to ask questions
Okay. Yeah.
or
Yeah. Yeah.
whatever.
Sure. Okay. So um,
What the f is going on?
what the f is going on?
All right, good question. I could have figured that out myself that was going to be the question. So one thing we learned trying to do a previous take of this video was that, well, I now have a better sense of how it works, so we can approach it a little better than the last time when I was just like, what's going on here? But so I think maybe the best approach to understanding this would be if we sort of deconstruct it and then reconstruct it in a fresh buffer here. So at the broad level, first I'll give a quick outline. So at the broad level, what it's doing is playing a melody a bunch of times where each you can imagine like a bunch of people singing a melody like row 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 your boat, and they're singing it. They all start at the same time, but they're all singing the same melody, but they're getting progressively slower. So one person is singing at a normal speed, the next person's singing twice as slow as that, the next person's singing a little slower than that, etc. So there's the biggest thing that we'll be looking at is, well, the melody itself. How did we generate that? And then we can also look at exactly how it's working in terms of stacking all those proverbial singers on top of each other. But the main man, this is almost harder actually than just trying to figure it out.
It is,
Yeah.
because there's that process of discovery has already happened for us, and it's like so now our memory. I feel like our memories are engaged, and it's like, oh, there was all of these things that we figured out.
Yeah.
So Jesse, you wrote this like more than half a year ago, or about that long ago.
Yeah,
right?
well, I mean, we sat down and wrote this together. I was the one
Right.
who knew the details of
Jesse knew how to write the code.
the
So
code.
Jesse's checking his phone, and I'm gonna I'll start to fill in the good people a little about how we came to this. We were exploring kind of overtones and frequency ratios of intervals. So if you've studied music theory, you might know that. This is much harder when we've done it once and we're like, oh, we want to say the same things we
It's
said
like now
last
we're gonna
time.
do a really good job. But
Yeah,
now
there's
putting
just
pressure.
like more things to remember.
I got an idea. So
Okay.
I'm gonna start moving stuff over into here and we'll
Okay,
just
yeah.
examine how it works. So
Sounds good.
I'm gonna start with this function here that we wrote. Paste. I'm gonna assume you know a little bit of code, or if you don't, that basically I'm not gonna explain how this whole thing works, but we're just gonna see what it does. Oops, one minute. Factors of, let's let's try 6. So what we have here is a function we wrote that returns the prime factors of a number. And I'm actually curious, I can't remember the exact format in which the answer comes back, so we're going to print that out and we'll see. Okay, so the prime factors of 6, we get a list.
Oh, right.
Yeah, okay, this is what I was remembering, but I wasn't sure. So we get back a list of pairs, basically. So it's a list of lists, and each of the inner lists has exactly 2 numbers in it. And the 2 numbers are a pair of numbers that multiplied together will give you the original number. So I'll just do one more example. Let's take something with more. In fact, let's do 30. I'm going to make this bigger. Okay, so 1 and 30, 2 and 15, 3 and 10, 5 and 6, and then all those same things with the order reversed.
Yeah.
So actually, this isn't even... I thought we were talking about prime factors. We're not even talking about prime factors.
Right.
We're just talking about any combination of 2 numbers that can be multiplied together to give you 30 or whatever number you care about.
And it looks like and I kind of remember this, that we made it so that it starts, within these pairs, it starts with the lowest number, which is 1, and then the next pair starts with a 2, and the next one starts with a 3, and they get progressively larger, so that the last one is 30.
Yeah. Yep, you're right. It is sorted that way. So we're using... So this is kind of the main sort of engine behind deciding what notes get played in our melody there. So let's explore how that process happens, which is going to come down to this function here. The control V, is it Windows? Yeah. Okay. Now this one's pretty nuts. This is somewhat ugly code. Oh, it's fine. So what's going on here? I actually am going to want to kind of deconstruct a little bit how this is working, unlike in this one when we just looked at what it does. But first I want to do the same thing. Let's just look at what it does. So print pairs. We have to give it 2 things. One, this max thing, and the other is frequency. So let's just say 10 is going to be our max, and for the frequency we'll do 360 hertz. And what are we going to get?
A bunch of many numbers.
We're going to get...
Is it like maybe make the max like really like 4 or something like that.
Okay.
Or 6 or I don't know.
What I'm also going to do, how do you dot length? Ruby, I can remember how to do Ruby. 26, that's how many.
That's how many, okay,
that's how many.
Nice.
So, okay, first things first, what this thing gives us back is a list. It gives us back a melody, basically. It gives us back a list of MIDI numbers, like you said, where each MIDI number represents a note on the piano. Although, with MIDI numbers, you don't have to be constrained to whole numbers. You can do weird decimal numbers, like as if you had a piano with infinite keys where there's like little keys in between the others.
And we have a little machine kind of that's in there that helps us with that Jesse will get to in the course of deconstructing this little snippet of code.
What machine?
Oh, just the hertz to MIDI function.
Oh, yeah. But I do want to do what you said, which is I'm going to make this number smaller so we can just get a feel for how this function's working. Well, and we get fewer numbers. We get 6 or 7. So let's just get to it, and then we'll see. But so, before I do that, so this thing is giving us our melody, and then maybe before we even look into this, I'm gonna show how we're using the melody. It's basically this part. And I'll give it this same data so we can So this Ruby function from the Sonic Pi API, play pattern times, is a function that if you give it a list of MIDI numbers, it will. A list of MIDI numbers and a amount of time between how to space them out. It'll play the melody where it plays each note with a gap of like half a second in between them. So let's hear that. Oh, okay.
It's using a different synth, I think, from the one that we had. In the
Right.
buffer.
So this sounds a little different from before because we're using a different synth. So if we want it to sound the same, we could do this. Cool. And maybe I'll even go ahead and move this up to 432, so we're starting to make it sound exactly like the other one. Call me crazy, but that sounds exactly the same.
We'll try it again. I mean, 360 and 432 are relatively.
Boom! Forgot to change that. All right. Actually, we don't even. Well, okay.
Can we quickly talk about why we use the number 432? Because I don't want people to get the wrong impression. Because there's a lot. 432 has a lot of baggage. Is the frequency, like, you know, some people.
Is it like a culty thing?
Oh man, I don't want to piss anybody off. I wouldn't say it's a culty thing, but people think.
Did you talk about the concert pitch versus the other thing?
Well, yeah, I mean, people think that, like, there are a lot of people out there who think that 432 should be how we define the note A, which is defined as, the concert pitch is 440 hertz. A lot of people think that 432 hertz, there's something that, that life would just be better if, that's not, I don't want to say one way or the other. We're not here to make an argument about 432A, but there's a reason why we use the number 432, and I just wanted to say what that reason is so that people don't.
Is this like a heated thing? People are going to be like, what the fuck?
We'll see.
432?
We'll see if they listen to that, I mean, people get intense about it.
Really?
I've never gotten in the middle of it, but I've just kind of seen some videos where.
Wow. Yeah. Okay, well, yeah, if you're a 432 or 440 partisan, we're
not affiliated.
We're not affiliated. But yeah, the reason we're using 432, and I'm guessing this is why some people prefer to use it, is that it's. We can actually do
print
this.
the factors.
Yeah.
It won't just do the primes, it'll print, but it's a lot. It'll be a lot.
Factors of 432. What did I do? I just clicked something weird. Go away.
Here, just go take the, let's see here. I think if we go up here and then say go away. Alright, sorry about that, folks.
Okay, we don't care about the sound. Oops, I did this afterwards, so it was going to wait and play the whole melody before it just printed the thing.
Well, basically, it's gonna, I mean, it's, what is it, 216?
Alright.
It has a lot of prime factors.
Here's our prime factors, folks.
So those are just all the, not even prime factors, that's all the factors.
These are all the factors.
It's basically going to be...
It divides evenly a bajillion times.
Yeah, it's 2 times 2 times 2 times 2 times 3 times 3 times 3. So it's 2 to the 4th power times 3 to the 3rd power. So it's got a lot of factors, and it's going to generate a lot of kind of whole number. And so when we were initially conceiving about conceptually about what you see in front of you here, 432 was a good number to use to think about it. And you could use other numbers, and it'll still do it. But
actually, since you brought us down to, now I'm really curious. Can we try a couple numbers?
Yeah, let's try it. Maybe it'll just,
What if we do 60, which is...
Do it. Try a prime number.
I want to do 60. Then
okay.
Hold on. Let's tell the good people. 60 is 2 times 2 times 3 times 5.
I think yeah.
Oops. 2, 2, 3, 5.
Yeah, it needs integers or else it does weird stuff.
Is it that it's lower? Like
It might, yeah, that might be it too. 60 is toward the lower threshold of.
Can we like do the thing and then shift it up or something? Because this is gonna.
Oh, I mean, you can multiply it times another number.
Like after the fact or whatever.
You can multiply it times like a decimal too, and you can get something.
I don't know if this is too far off track, but look, man, if anyone's watching this, who the hell knows what they like? Because this is a weird thing to be watching. You guys are weird. App times 4 or something should be good. Or no, actually, bigger than that. 8.
We're gonna return from this tangent very soon, folks. Bear with us.
No, don't bear with us. Just have.
All right, yeah. Just
You're
be
having a
patient.
blast.
Check it out.
Yeah.
Do a Google search if you need to.
All right. I don't know what I'm. All right. Clearly, this isn't working.
Put in start it instead of 432. Put in like a 432.5 and just see if it explodes.
I have a feeling it's. Okay. Yeah.
Okay, it still does it.
I was wondering if that was gonna happen.
How does it factor it? Does that one need to be 4?
No, this one's just printing.
What? Okay.
Let's see what it prints. What?
Doesn't like that.
That's
Doesn't like to
bizarre
print them.
because it should be the same. All right, if I'm calling pairs, then I'm calling factors of. Oh! Dude, the frequency doesn't even really matter. It's because the thing that gets factored is 2
and then it just
up through
multiplies it
this
times
thing. Yeah.
of starting frequency.
Yeah, so I think really the reason we did 432 is just so that when we were debugging and printing stuff out, we would get integers instead of these big numbers.
Okay.
Because really we're just making a bunch of ratios and then multiplying it by whatever you want.
I wonder if there was somebody who's like watching this video who like could look at the code and realize that that was the case and was just like, no, you idiots, like you're saying the wrong thing.
Yeah,
Quite
could be. They're probably like, what the hell is going on?
Well, we figured it out.
So,
do we want to start over or do we want to keep going?
I don't know. Let's have a vote. Let's let the audience vote. Do you want to start over?
We could.
Every second we spend deliberating about whether we start over makes it more likely that we should start over.
Let's keep going.
Okay,
All
here
right.
we go. So what should I talk about now?
Okay. Well, let's go back to buffer 0 and see if there's a, So what did we do? We just figured out what? What did we just figure out?
We just figured out. Well, we went on this thing about why we're using 432. And we realized it doesn't really matter. But before that, we were.
Were we on track before that, or had we like said something that was wrong? I think you were. I think it was. I think it was because I called out the 432 thing. That was me. Sorry, guys. So we could just try and pick up from where we left off.
Okay, let's pick up. So we're generating this melody, then we're playing the melody. That's simple. The question is, how do we generate the melody? That's where that's where all the secret sauce is in how we're generating the melody. So let's look into that. So I'm actually going to comment this out so we can do more just print statements without making a bunch of ruckus. What I'm going to do is slowly add onto this function. So let's ignore this. I'm going to print the melody that comes from And honestly, this is a weirdly named function, calling it pairs.
Mm-hmm.
Very weird. We should call it, I'm going to do this right now. I'm going to call it create melody. Create melody. Okay?
I can dig it.
Now let's see what happens. So if I get rid of everything, it gives us a range of numbers 2 through 4, which I'm sort of annoyed that it Ruby treats a range, it's some distinct object. It's different from a list.
Okay.
But really what we're talking about here is we're talking about a list of numbers, starts at 2 and goes up to whatever you put here. So if this was a 10, God damn it, you make...
Yeah. By the way, yeah, if like just take the, if it comes up, come up here and say go away.
Okay.
Sorry, I should have just like closed all this stuff out before we started this.
So we've got these numbers. So you can imagine what this really is a list of numbers 2 and 3 and 4 and 5 and 6 up through 10. Now I'm going to slowly add more things on, and we'll see what the thing is actually creating. Let's do this. Okay, and I'm going to make this a little smaller. Let's go back to, let's do 5. So what we have at this point, we just passed in 5 and 432. The 432 isn't even being used yet. It doesn't get used till the very end, so don't worry about that. So what are we doing with this 5? What we're doing is we're finding all the factors of all the numbers starting at 2 up through 5. So we've got the factors of 2, the factors of 3, factors of 4, and the factors of 5. And for each of those numbers, when we're looking at the factors, each factor, if we zoom in, is a pair of numbers like we saw before. This is the two numbers that multiply together to give you 4 or whatever number you're looking at.
Got it.
Then what we do is we flatten down one level. In other words, what I have here at this point, what we have is we have a triply nested list. We have a list of lists of lists. Because we have a list of things. Each thing is a list of the pairs for each number. And so what we want is, we don't care about distinguishing between the pairs associated with 2, the pairs associated with 3 and 4 and 5, etc. We just want them all together. We don't care about knowing that some were grouped together. So we're going to flatten out one of them. So we'll go from a triply nested list to just a doubly nested list. We're going to have a list of these pairs. So, as you can see, I wasn't lying to you. Oh, well, that's crazy. Let's do this again. Got a list of pairs. A 1 and a 2, a 2 and a 1, a 1 and a 3, a 3 and a 1, 1 and a 4, a 2 and a 2, etc. Next, we do the thing that we really wanted to do the whole time, which was, for each of these pairs, we're going to turn that into a fraction, like 1/2, or 2 over 1, or 1/3, or 3 over 1, or 2 over 2, or whatever, and we're going to multiply that by our frequency. And that's going to give us the frequency of the next note in the melody. And then the other thing we do is we convert the frequency to a MIDI number, which actually, you know what, that could even be, maybe I'll simplify that so we do fewer steps at once. Just going to map again. So this is going to give us, well, I'll just stop here. This is going to give us a bunch of fractions. Oh, no, sorry, a bunch of frequencies.
No, because it already multiplied. It took the fractions, then it multiplied the fractions.
And you know what? You know what? Let's really break it out, because that's what understanding is about, is breaking this down. So this is going to give us a list of fractions. And they're weird fractions because I'm going to move this 5 up to let's do 9. So then we should have, I'm going to do 10. Oh, this isn't what I expected, because what I expected... Oh, we're getting an error. Our code is super buggy. This is fascinating. We're discovering in real time, because when I change this thing, it's going to do what we actually want it to do, which it's never done before. because so here's what's going on.
Okay.
Every time we're dividing a small number by a big number,
Yeah.
it's giving us 0
Oh.
because it's rounding them.
Son of a gun.
Son of a gun. So we need to convert this thing to a float instead of an integer.
So is this going to give us a completely different sounding thing?
I think it will.
Oh, interesting.
Let me see if that works.
Sorry.
Yeah, look at that. So now we have a list.
Dude.
Now we have a list of fractions.
Okay. So, wow. Oh, this will be interesting.
Well, I almost want to hear what it sounds like now,
Yeah.
but let's not. Let's hold the suspense even for
Okay.
ourselves.
Oh man, it's killing me.
This is killer content. This should be behind a paywall.
Yeah.
Okay. So we've got our fractions. Now what we want to do is map the P. Oh, P stands for pair. What's a F stands for fraction. These stupid one-letter names aren't very good, but that's okay. Fraction times the frequency. We've got our fractions. Now we want to get, what we really wanted to do is put them all in terms of some root frequency. So this is giving us 432 times the first fraction, 432 times the second fraction, etc. So we have a bunch of these frequencies that are around a nice human hearing range. Finally, instead of frequencies, what we want is, I'll do another F for frequency. Actually, I'm gonna go ahead and just give it a good name. Oh, I can't call it frequency because we already have that thing. Forget it. This is fine. Don't worry about it. We're gonna do hertz to MIDI of the frequency, and this will give us a MIDI note number. And I'm gonna assume people know what that's about. So 56 point whatever, that's a MIDI note. 80 point whatever, that's a MIDI note. 49, etc.
So MIDI note is just converting the frequency into a form that the computer can kind of understand and deal with. Is that relatively?
Yeah, I mean, and sometimes the computer can deal with frequency, but just in terms of how this exact Sonic Pi function works. If you want to use this play pattern thing, you give it MIDI numbers. It doesn't want frequencies.
Right.
Yeah.
So there's a function that will take a frequency and convert it to a MIDI number for you. Which we
just use. Yeah. Hertz to MIDI. Converts hertz to MIDI. So now we have our actual melody. And okay, now is the time in the video where I naturally would have played this thing anyway, so we can go ahead and hear what it sounds like.
Hear what it sounds like, yeah. It's gonna be interesting.
Now do we want, let's do this. Let's do 10 and 432.
Okay.
So it sounded pretty similar, actually, to me.
Yeah. You want to speed it up and see what? Or?
I almost want to, like, can we even tell the difference here? Am I crazy or? I'm telling you, this is the same thing. Because if it's a 0, like, I don't see any zeros here.
Oh.
Now, here's the zeros, negative infinity. So what the hell's going on?
Do you think it's just skipping those? But then it seems like it would sound different.
It would sound different.
Do this. Speed it up a little bit, because I think our brains will be able to compare.
Yeah. I think this is the same as how it was.
Okay, so play that. Okay.
And then, yeah, I mean, you would hear a rest every other one.
Yeah.
Am I crazy or are we
So
not?
can we change it back so that it doesn't?
Oh, check it out. Look, this is our list. But like, once you look at the notes that are being played, because it prints out whenever it does something.
Right.
It's playing that 56, even though it says negative infinity here. So it actually
Just
does
like
sound.
condensing it.
It's somehow it's presenting in one format, but somehow it does know
Well,
still.
It's that's interesting.
So basically, we don't get to hear a new song.
Oh, okay.
What we've been hearing was the right thing all along.
Interesting.
Yeah. It's weird. I'm still gonna put this back because it feels more correct. But okay. So hopefully it kind of makes sense. What's happening here? We broke it down. To summarize, let me see if I can summarize it. We're multiplying the root frequency by a bunch of different things. And those, by a bunch of different simple whole number ratios, which is what makes shit sound good a lot of the time. And the way we get those ratios is by looking at a bunch of low integers, like 2, 3, up through something relatively small, and just taking all the combinations of simple integers that are present in terms of factors of these numbers. So we're just getting a big soup of these integers, of these simple integer ratios, and then multiplying them by the frequency, by the original frequency that was passed in. The only thing left in terms of getting from where we're at here to where we're at in the final thing is this was actually 100, which gives us a longer melody, and also you'll notice that the melody gets weirder and weirder as time goes on, because as this number gets bigger, the factors involved in producing a bigger number are going to be farther and farther away from really simple, normal sounding stuff like 2/1 or 2/3.
So it's that. I think it's that, and that like some of the you can get like kind of more complex fractions, and you also just get like much higher and much lower notes than what you're starting off with.
Right, much higher and much lower notes. So this is one thing that's different from the example, but now it's up to speed with the example. I guess we'll play this. Cool, that wasn't actually even as long as I thought it would be.
Yeah.
The thing that makes this one epically long is that we not only we don't just do the melody once, we do that stacked voices thing, and that's what's going on here. So we're playing the same melody 64 times, and each time the only thing that's changing is basically this duration number, which gets passed into this, which tells it how much to space apart the voices. So
where does that happen? Where is it the spacing out?
In a thing that I haven't pasted yet.
Okay.
Yeah. So I'll combine them instead of doing this do the thing. I'll just paste this directly in here. Copy. You know what? I'm just going to type it. So I'm going to take this thing that we had, cut, paste, and instead of 0.25, I'm going to do n. So n is going to be 1, then n is going to be 2. Or, wait, hold on, sorry. Yeah, that's what I'm going to do. And this is almost what we need. The only other thing is that we want these voices to be happening all at the same time. We don't want to. What would happen if we did this? If we did it just how we have it, it would play the whole thing, then it would wait till it's done, and then play the next one slower. Wait till it's done, and then play the next one slower. But we want them to all start at the same time. So I'm going to put each thing in its own thread. In thread, do this. that thread thing make sense?
Yes, it does to me.
Cool. And this, I believe, is going to give us the same. We've rebuilt the entire thing. There's actually one more thing, which is that it's going to be slower. We'll fix that after I do this. Wow. That was way slower than I thought. So I don't know. We'll see if I actually was expecting the only thing that we'd need to do is paste this. But given how slow that was now, I'm not so sure. So I don't know. We'll find out. Here we go. Oh, something's going on here. Let me see.
Sustain, maybe?
Oh, maybe you're right. Okay, let's give it the same sustain as before. 0.25. This just tells it how long to hold that note. I don't.
So there should be more. Oh, okay.
That was
like
it.
that.
You nailed it. All right. Cool. Yeah. So the reason we stack the voices like this is because it sort of allows it to, as the first one's getting off into a weird land of strange ratios and like really high and low notes, it's getting harmonized by what's coming behind it more slowly, which is in turn getting harmonized by what's coming behind more slowly. So this overall thing is going to go on forever. Like, I don't know how long, probably, I don't know, an hour or something, because like the slowest one's happening 64. It's like one note per minute or something.
Right. And then there are how many notes?
I have 26 or something.
Okay.
Oh, and this is actually this. Okay, we didn't even have it how it was. Now we do, but yeah, I don't know. There's a lot of notes. Oh, let's find out how many notes there are. Print melody length. 481 notes.
Okay, so it's that many minutes, right?
It's that many minutes. It's a long time.
So it's a long time.
It's like half a day or something. Anyway, but so now we've this is our little algorithm for creating that little song.
Cool. Should we? You want to like up the BPMs to like 450 and then just let it play for 30 seconds or so?
Yeah. All right. So this is gonna be super fast. See how that sounds.
So yeah, hope you enjoyed it, and you stuck with us to the end. You're a champion. We're thinking about maybe making some more of these. We've actually kind of co-authored a lot of these like kind of little music generator things, and this is the first time that we've really tried to present them in a video format or in any format to the general public. But yeah, we'll see. Throw this up on my YouTube channel if we don't encounter too many technical difficulties, and see if people watch it, if people appreciate it, and yep. Any final thoughts?
Thanks for watching.
Yeah.